Okay, on this function we have a piecewise function, and we can, again, describe intervals of increase, decrease, and constant. But what's really interesting on this one are the max and the mins. I mean, clearly, no problem that that right there is a relative min. And it occurs at the point 2, -3, it looks like. What's interesting about this is depending on which book's definition you're looking at, sometimes they'll refer to a plateau like this as a max or a min, but by most definitions that's considered that whole region is called a max still. So this whole region right here is called a relative max, not just the center, but the whole line. All right, so we'll come back to that in just a second. Let's talk about intervals of increase and decrease. Again, you always start at the left-hand side, and you can see here I start by moving upward. And so when I start at the graph, that starts at -infinity. So I'll start at -infinity, and it'll increase all the way up to -3. And then it levels off, and it's constant. Then it decreases, and then right here again at x equals 2, it starts increasing again. And it looks like it increases to forever after that. So union, it also increases from 2 to infinity. All right, now decreasing, if you look at this function really carefully, it went up and then it leveled off, and then right here at when x was -1, it decreased. So it decreased from when x was -1 all the way till x was 2. And then it was constant from the range from -3 to -1. All right, so and again, as far as like that goes, this whole thing represents a relative max, this whole line right here where it was constant. And the last part is the end behavior. It suggests as x moves forever to the left, so if you basically start the y-axis and move to the left, it kind of moves up, moves down, but what it ends up doing, the further you go to the left, the further it goes down, and so that goes towards -infinity, and that would just mean down. And as I move on the function to the right, which means as x approaches +infinity, as we go forever to the right, it goes up for forever, and so that would be towards +infinity as it goes up. Okay, now we're going to try looking at these same things using applications. A person is building a Lego fence for his model farm. They have a total of 12 Lego blocks, and they are 3 centimeters in length. The builder is only using 12 blocks to create the rectangle as shown below. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and didn't need to have them meet at the corners. What are the possible configurations to build the rectangular border such that there's at least some area that is enclosed? Now let's try to think about this. Let's use just one block this way and then one block this way. So out of the 12 blocks, I just used up 2, so I have 10 blocks left over. And that would mean that I can make 5 going in on each side, 2, 3, 4, and then 5, and then 1, 2, 3, 4, and 5. So you can see I have one block this way, and I have 5 blocks this way, and if you count, there are exactly 12 blocks that I used to create that. So in this case, each one of these is 3 centimeters, so if I think about each one of these being 3, the dimensions of this, let's call this the length. The first possible length that would actually enclose some area would be 3 centimeters by, and if you count 3, 6, 9, 12, 15, so if you add up 3 times 5, you get 15. So the width is 15 centimeters. And to find the area is given as length times width. So 3 times 15, if you multiply that, that would be 45 square centimeters. All right, so that's one possible such configuration where I used all 12 Lego blocks for that one. Now let's try another one. The next one we could do is maybe use 2 blocks this way. That's exactly what's up here, and then 2 blocks this way. And if you think about that, I've used up 4 of my 12 blocks. So if I do 12 minus 4, that would be 8 blocks left over, which means there have to be 4 on each side. So 1, 2, 3, 4, 1, 2, 3, 4, and that's precisely what we have up here. Again, each one of these lengths are 3 centimeters. So in this case, the length is 6 centimeters. And the width in this case is 3 times 4 is 12 centimeters. You add up 3 plus 3 is 6, plus 3 is 9, plus 3 is 12. And again, we'll do 6 times 12. In this case, we'll get 72 square centimeters. So we got a little bit more area that time using the same number of blocks. All right, let's erase this one and try another one. Now maybe I could do a shape where I have 3 going this way and 3 going this way. All right, so now I've used up a total of 6 blocks of my 12. So if I do 12 minus 6, that leaves me with 6 for each side, and I got to divide that by 2, so that would be 3 on each side. And so if you count this, I have basically 12 blocks going around, and each of them are 3. So the length in this case, would be up and down, so that would be 3 times 3, which would be 9 centimeters. And then again, we'd have 3 going this way, so it'd be 3, 3, 3. That would also be 9 centimeters. So that would be 81 square centimeters. So continuing this idea, instead of using 3 on the length, I could also use 4 pieces. 1, 2, 3, 4. But if I use 4 here, I also have to use 4 on this side. So if I think about 12 minus 8 blocks that I've used, I've got 4 left, and that means there needs to be 2 on here and 2 here. So that would be 3, 3, 3, and 3 for the length. So that gives me a total of 12 centimeters now for the length. And it only gives me 6 centimeters for the width. If you look, that's actually just the flip of these two right here. So it's still 12 times 6 again. 12 times 6 is 72 square centimeters. And then there's maybe one more configuration that I could use. Instead of having 3, I could use 4 blocks going up and down. 1, 2, 3, 4. 1, 2, 3, 4. And I've used up, in this case, I've used up, count, we've got 8 blocks used up there. Actually, I could go 5 blocks, I'm sorry. I just did 4 blocks last time, so I could use all 5 blocks. So that would be 12 minus 10, which would equal 2. So I only have 1 left for each top and bottom, so that would be 3, 3, 3, 3. So in this case, 3 times 5 is 15 centimeters for the length. And 3 centimeters for the width. So 15 times 3, that would be 45 square centimeters. And I really can't do anything else with that, because if I go up and use 6, 1, 2, 3, 4, 5, 6, and I use 6 on this side, I don't have anything left to put a line going across for the width, in which case it said I had to have some area enclosed, and this would have 0 area enclosed, so that's not, because the 2 sticks would be side by side, there'd be nothing left. So I think I've come up with every possible configuration that we could come up with for length and width, given those set of 12 Lego blocks. So it asks, what is the maximum possible width in centimeters of one of the possible rectangles with at least some enclosed area? Alright, so if I look here, I'm just looking for which is the biggest possible width, and it looks like we can have basically 15 centimeters, which used 5 blocks. What is the minimum possible width in centimeters of one of the possible rectangles with at least some area enclosed? So it's asking which is the smallest width, and that would be 3 centimeters, which used just 1 block. Alright, what is the maximum area that could be enclosed with the 14 Lego blocks? And if you look here, now we're looking for just the maximum outcome. In this case, it was 81 square centimeters. Alright, I hope that was helpful. Again, please ask your teacher if you need additional help with these.